So the colligative property is the property of a solution that differs from the property of a solvent. Blah, 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 blah.
Hey y'all, and welcome back to the Joy of Solutions. I'm your host, Rob Boss, and today we're going to be mixing a doozy up. Today, my friends, we're going to be reducing the concentration of some acids, but for those of you who haven't been around here before, we're going to need to talk about how to describe those concentrations. We're going to start off with my favorite part. I'm going to beat the devil out of our little brush here. Just get real nice. First, we could use molarity, which is the number of little acid particles in moles per liter of solution. Next, we could use molality, which is the number of little moles of acid per kilogram of solvent. Now, mass percentage is the percentage of mass of acid per total, while mole fraction is the same thing, but percentage of particles. Just go ahead and beat the devil out of it.
Hi, welcome to The Cook, starring me, The Cook. And today we're going to be making my favorite rock candy. Now, the process is pretty simple. Take a little bit of sugar right here, and you put it inside our water. Now, sugar is held together by covalent bonds, which means this solution right here is a molecular solution. If you're playing with something like table salt, which is ionic bonds, then it would be an ionic solution. Easy as pie. Now the key to making rock candy is to get the sugar past its traditional saturation point, the point at which no more sugar can dissolve in the solution. Now there's a couple ways we can increase the saturation point. We can irritate it, which we have been doing by stirring. We can increase the surface area, which we can't really do, we already have granulated sugar. Or we can increase the heat, which is what we're going to be focusing on today. Now, when you increase the heat, the molecules move faster, which means they dissolve easier. So you can put more sugar in the water. This solution is considered supersaturated, and as it cools, the sugar crystals will begin to settle out, and that's what we call our rock candy. Now, we're going to let this cool for a little bit, but in the meantime, we're going to make ourselves a little drink to go with our rock candy. Now, personally, I like drinks that are homogeneous. So we're going to need two liquids that will dissolve each other. Now, here in the kitchen, we have a little saying that like dissolves like, which means that liquids with similar intermolecular forces are more likely to dissolve each other. Now, oil won't dissolve in water. Its London dispersion forces don't mesh very well with water's hydrogen bonds. But acetic acid with its ionic bonds, or as we call it in the kitchen, vinegar, will mix with traditional water very, very well. The two are miscible. They dissolve each other. Now that's pretty good. Come in!
Sheldon, I need you to teach me colligative properties.
All of colligative properties?
Just enough to engage with Leonard.
Alright, now this should be pretty easy for you to learn.
Oh really? That's awesome.
Bazinga! You fall prey for another of my countless practical jokes. Now listen up. Well, first we're going to have to learn what colligative properties are.
Okay.
Anyways, colligative properties are properties of a solution that differ from the initial solvent. Now, an example of something that would exhibit colligative properties is sodium chloride dissolved in water. Now, sodium chloride has a Van Hoff factor of 2. It dissociates into sodium and chloride. Now, an example of something with a Van Hoff factor of 1 would be a disaccharide, like sugar.
What?
Penny, please don't interrupt me. Now, some examples of colligative properties are...
Hi, I'm Jason.
And I'm Regis.
And welcome to Blockhead.
Woo! What are you doing? Get water hot, dump it on someone. What? You know you could keep it a liquid, but make it hotter. How?
If I put 6 moles of salt into this here kilogram of water, we're going to end up with a 6 mole solution. And since your boiling point of your solution is elevated by your Van Hoff factor
Times molality.
times your boiling constant. Well, we know the Van Hoff factor is 2 because it's table salt. We know the molality is 6 because we calculate it up here. And the boiling constant is given to us as a 0.512. Now, all that together, that's going to make your water about 6 degrees Celsius hotter.
Sweet! I'm gonna ride this wagon into that lake!
But it's frozen.
Let's just add salt again.
But I thought that just raised the boiling point.
Nah, man, it'll lower the freezing point too. Just add.
If I add 6 moles of salt for every kilogram of water in the lake, then I get a 6 mole solution once again. But for this one, you gotta use the freezing point constant, which is 1.86 for water. And then, turns out, you get about 22 degrees Celsius colder water before it freezes.
So it'll still be a liquid?
Exactly. Let's get some.
Give me that.
Hey, I was watching that.
We still haven't finished going over colligative properties.
Fine.
Now, where was I? Oh yes, examples of colligative properties. Now, one example of this is the vapor pressure of your liquid lowering. Now, every single liquid has a vapor pressure, part of it that evaporates into the atmosphere, regardless of temperature. But when you have a solute in there, then you have all these intermolecular forces which will prevent some of that from evaporating. Now, a great example of this is alcohol, which is known for evaporating very easily. Now, if you put a little bit of solute in it, then it won't do so as readily. Now, a final example of this is osmotic pressure. If you have a semi-permeable membrane, the higher concentration of one solute on one side than the other, then some of the liquid will go across that semi-permeable membrane to equal that out. Red blood cells need to be kept at a very specific concentration, otherwise too much water will go out or in, and that will cause the cell to either shrivel up or get too big and pop, also known as cytolysis. Have you got all that?
What?
We'll fly the colloids, guy.
We all know about the salt water in our oceans. But what happens if you mix sand into it? Why do they behave differently? The salt is completely gone, but the sand, it's still there. See, chemists will actually call these examples two different things. See, the sand, it's just too big. It won't dissolve, and it just suspends there temporarily, and that's what we call it a suspension. But the salt, well, it fits through without any problems. But the cool thing is, there's a small area between the two, one where the particle doesn't dissolve all the way, but it doesn't just settle out, and these are called colloids. See, a colloid, well, it's not really a liquid anymore, as you can see. It's pretty magical. The neat thing about colloids is that light doesn't shine through, but the salt water, it shines through easily. This is what we call the Tyndall effect. See, the Tyndall effect says that light disperses from the colloidal particles suspended in the solution. And some colloids, well, they're pretty tasty.
This episode of Will Fly is brought to you by the following sponsors.
Tired of lame, sad salad? Then stop eating it! Billy Mays here! Try new Billy Mays emulsified salad dressing. With emulsified technology, the layer of oil and vinegar dissolves right out. Now you try. To show you the amazing powers of Flex Seal, I'm gonna rip this piece of paper in half.
Please note that actual Flex Seal is sold inside of a colloid known as an aerosol, where the liquid is suspended in a gas.
Amazing!
Howdy, kids. Come see our new crazy, wacky super goo. You'll never see anything like it in your lives. Our goo is made of a special kind of a colloid called a sol. It's a solid suspended in a liquid.
The end of our review. You gonna be ready for the test, Jason?
Yeah, I think so.